So we've seen what happens if I have a source of charge here. We've seen what electric field it creates. But what happens if I have more than one source of charge? Suppose that's only the first source of charge. Suppose there is somewhere over here another source of charge, which I'll call QS2. And maybe over here there's a source of charge QS3. And let's just say that this one is negative. And maybe over here there's a source of charge QS4. And I'll make that one positive again. And there's many more. And here is the nth charge, and we'll make this one negative. So I have a bunch of sources of charge, capital N of them, in fact. And now I want to ask, what is the electric field caused by all of these charges at some point? And, well, I'll put the point P, maybe I'll put the point P right there. So the question that I want to ask is, what is the electric field E at the point P, not caused just by one source, but caused by all of these n different sources? And the answer to this question is something that we know only from doing experiments. It's the last piece of our fundamental understanding of how Coulomb's law works, how electric fields are created, is to understand the answer to this question. And you can't derive the answer to this question from Coulomb's law as I've given it to you. This is a further fundamental fact about the world that we live in that we've learned by doing experiments, by making observations of how the world works. And so here's the answer. I'm going to tell you the answer now. So if I want to know what the electric field is at the point P, I start by saying, well, what's the electric field at the point P caused by this source of charge QS1? And we saw that that will be a vector pointing in this direction here. So, okay, maybe that's going to factor into my answer in some way, so let me write it down here. I've figured out what the electric field at the point P is caused by the source of charge S1. Now let me keep going. Here's source of charge S2. That makes an electric field at the point P, which, because I'm so much closer, I'm going to draw as a bigger vector. It's pointing in this direction. And I work that out as a vector. That's the electric field at the point P caused by the source of charge S2. Well, I keep going. Here is a source of charge S3. This one is negative. So this negative charge will create an electric field at the point P that points towards the charge. So it's a vector pointing this way. And that is the electric field at the point P caused by the source of charge S3. Well, then I have QS4, so I have more charge over here. This source of charge QS4 is going to make an electric field at the point P. That's pretty small. It's so far away. It's pretty small. It's pointing this way. And I've calculated that vector, and I write it down. It's the electric field at the point P caused by the source of charge S4. That's another vector. So I've got 4 vectors written down here. And then I get the last 5, 6, 7, 8, 9. So there's going to be more vectors written down here. And then I get to the nth one, source of charge here, QSN. That will create an electric field at the point P, which is pointing in this direction towards the source of charge because the source of charge is negative. And so here I have my nth vector, the electric field at the point P caused by the source of charge Sn. Now, what is the actual electric field at the point P? The answer is that it's the vector sum of all of these vectors. I take all of these vectors that I've worked out and add them. So I take all of these vectors and add them. And if I do that, you can see that the way I laid out my charges and where I put my point P, when I vector add these 5 vectors, I'm going to get a vector P. Here's my point P again. And the electric field is going to be pointing in approximately that direction. So the electric field at the point P, which is what I was asking for, is given by the vector sum of the individual contributions to the electric field caused by each of the sources of charge individually. Now, this may sound obvious to you, but I really want to stress that it doesn't have to be this way. And in fact, there are fundamental laws of nature which don't work like this at all. If I was teaching you not about electric forces, but I was teaching you about the force between quarks, the force between quarks does not add in this way. If I have a quark here and I have a bunch of other quarks around it and I want to know what's the force on this one quark, you can't do it like this. It doesn't work this way. So this is it feels simple and straightforward, and it's what you all expected, but this is a fundamental fact about electric forces, which didn't have to be that way. We had to learn it by doing a series of very precise experiments, which have been done over many years. And last thing I want to say is that the fact that the electric fields add like vectors, that's telling you that the electric forces add like vectors. Because remember, this electric field is telling you what would the force be on a test charge that I put right there. And the fact that the electric field is obtained by vector adding these contributions to the electric field tells me that the force on this test charge is obtained by vector adding the force on this test charge caused by this source plus that caused by this source plus that caused by this source. So this vector addition principle applies to the electric forces on a test charge at the point P, just as it applies to the electric field at the point P. So the principle of superposition that I just finished explaining to you is the last part of the fundamental description of how electric forces work. Once you have Coulomb's law at your disposal, which we have then reformulated in terms of electric fields, and once you have the principle of superposition, which tells you how to apply Coulomb's law, or how to figure out what field is created not just by one charge but by many, you now have all of the fundamentals that you need in order to understand how electric fields are made and what they do. And we'll stop there for today.